In the last video, we saw a problem with maximum likelihood estimation for n-gram language models. If we have an n-gram in our test set that was not in our training set, such as I like, the probability of the test data will be 0. In this video, we'll talk about smoothing, which helps to avoid zeros due to unseen n-grams. The idea of smoothing is to use some other estimation method that leads to distributions that are less peaked and more smooth, with the goal of having fewer zeros. But we don't just care about removing zeros. More generally speaking, we want more robust estimation methods that provide better handling for rare events. The simplest method is called add-1 estimation and consists of adding 1, or some other small value, to all counts. It's also called Laplace smoothing. Here's the MLE estimate for our bigram model, and here's the add-1 estimate. We end up adding the vocabulary size to the denominator so that the distributions normalize correctly. This is simple and avoids zeros, but it doesn't work all that well in practice, so it's not commonly used for n-gram language model smoothing. Most smoothing methods used in practice are some form of backoff or interpolation. These are related methods that combine multiple n-gram sizes in the same language model. A trigram backoff model would use the trigram probability if that's non-zero, and otherwise will back off to the bigram model if its probability is non-zero, and otherwise back off to the unigram model. Interpolation means using all n-gram models together with appropriate weighting, and this tends to work better than backoff. Here's an example of interpolation. The idea is to estimate unigram, bigram, and trigram models using MLE, then combine them in a weighted mixture, where the lambdas are non-negative weights that sum to 1 and can be estimated using development data. A more complex version makes the lambdas a function of the conditioning context. This can capture intuitions like increasing lambda for the trigram model when the bigram count is large. A widely used and highly effective smoothing method is Kneser-Ney smoothing. There are a couple of components, including absolute discounting and interpolation with continuation probabilities, both of which we'll discuss. The best variant is something called modified Kneser-Ney smoothing. This is the version most often used in practice. Absolute discounting is based on the following observation. Say you divide your data in half, and for all bigrams that appear in one half, call it the training set, you check their counts in the other half. This table breaks down bigrams according to their counts in the training set. Bigrams in the training set have slightly lower average counts in the held-out set. That is, their counts are overestimated. Bigrams that are not observed in the training set have counts that are underestimated. This suggests a way to smooth. Subtract some constant d from each numerator count. Use the original counts for the denominators. When doing this, there's some missing probability mass because the numerators are getting smaller, but the denominators are unchanged. So there's an interpolation with the unigram term p of x, and the lambda function is defined so that things normalize properly. The other component of Kneser-Ney smoothing is to use continuation probabilities. To get the idea, consider predicting the next word in this sentence, and suppose we're interpolating bigram and unigram distributions. In the unigram model, the word Kong has higher probability than the word glasses. But Kong tends to appear in a very limited number of bigrams, mostly Hong Kong. By contrast, glasses follows a wider variety of previous words. And more generally, when we're interpolating bigram and unigram distributions, we would expect the unigram probability to be most useful when we have not seen the bigram. That's when we really need to rely on the unigram probability. So, instead of just using a unigram distribution, we want to capture how likely it is for a word to appear as a new continuation of the previous text. The continuation probability of a word x tells us how likely x is to be a novel continuation of the previous word. So this probability will be proportional to the number of unique words that appeared right before x in our data. Then we'll normalize this using the total number of bigram types, that is, the number of unique bigrams. Then, Kneser-Ney combines absolute discounting with continuation probabilities when interpolating with the lower order distributions, where lambda is again defined to ensure things normalize. And while this is the bigram version, there's a similar recursive form for higher order models. When scaling up n-gram language models to web-scale corpora, Kneser-Ney smoothing becomes expensive, and so researchers have found they can use simpler smoothing methods. In a well-known paper from 2007, the Google Translate team proposed a very simple method called stupid backoff, so named because they assumed it wouldn't work. But it's so simple, they tried it and found it to be surprisingly effective. Here's the recursive function for computing an n-gram score with this method. It's not even a probability because it's not normalized. But since normalized would involve more computation, they don't do it and just use unnormalized scores. Since they were using this for machine translation, they didn't actually need a well-formed probability distribution. They were using it to compare multiple translations for a given input sentence. The scores use the maximum likelihood estimate if the n-gram was seen, and otherwise use 0.4 times the same score function computed using a shorter context. An important detail about smoothing: the smoothing methods we described only help avoid zeros for unknown n-grams where n is greater than 1. If there are new words in the test data that we've never seen before, then no amount of smoothing is going to help. The probability of the test data will be 0. Therefore, we must know the full vocabulary ahead of time on which we're going to be tested. There cannot be any surprise word types in the test data. This is described as a closed vocabulary language modeling setup. But this is not a very realistic assumption, so the alternative is to consider an open vocabulary setting, in which we create an unknown word symbol unc. We can replace some rare words with unc and treat it like any other word during estimation. Then we replace any new words in the test set with unc, and the probability of the test data will not be 0. There's a potential issue then when comparing two open vocabulary language models. If they have different vocabularies, then their unknown word symbols correspond to different sets of words. This leads to a bias in favor of the model with the smaller vocabulary. Consider the extreme case, where the vocabulary is just unc and the end of sentence symbol. We can define a bigram model like this that will achieve extremely low perplexities, but it's a useless model in practice.